Bismillahirrahmanirrahim. In this video, we will discuss about the selected harmonic elimination PWM technique. With the help of this PWM technique, we can eliminate 3rd, 5th, 7th, 9th harmonic from the spectrum of the output voltage waveform. You can eliminate any particular harmonic from the spectrum by adjusting the pulses or the notches as we discussed in the previous videos. So we will discuss about the implementation of the selected harmonic elimination using the Matlab in this video. So just look at this circuit diagram. In this you can see an H-bridge circuit that is shown over here. We will use this H-bridge circuit to generate the required output voltage waveform across the load. So we are going to use this resistance as a load. These are the power electronic switches, maybe the MOSFETs, maybe the IGBTs. So all of these are the power electronic switches. Right? This is the voltage measurement block. It measures the voltage across the load and display that voltage on the scope. This block stores the variable in the workspace. So this is basically two workspace block from the Matlab toolboxes, and the name which is specified over here, that is F, that will pick up the signal from this point and will store in the workspace of the Matlab. Okay, now if I look at this side towards the left, so here you can see the controller. This controller generates the pulses for the positive half cycle, and then you can see this second controller, this generate the pulses for the negative half cycle. So the pulses are generated from here, and the data type for those pulses is the boolean, either 0 or the 1. Let's suppose that this is the pulse waveform that is being generated from this controller block, and similarly from here we will be getting a set of pulses. So what is the function of this block? This converts the data type in the Matlab Simulink. So whatever is the data type over here, that will be converted into the data type which is required in the upcoming block, and that is the summer block over here. So if the double is required, it will convert it into a double one. If an integer is required, it will convert it into the integer. So this is the data conversion block in the Simulink, right? And we have displayed that signal over here at the scope. Now how this circuit is going to work, before discussing, let's go towards the output voltage waveform of the selected harmonic elimination technique. So let's suppose that we want to cancel 5 sets of harmonics. So we will have to introduce 5 notches in the output voltage waveform. So I have assumed the time period of 0.02 over here, that is 20 millisecond, that corresponds to the frequency of the 50 Hz. So this is the half time period. So in terms of angle, you can say this is pi. Now here you can see the notches. The first notch is introduced, let's suppose, at angle alpha 1. The second notch is introduced at angle alpha 2. The third notch is introduced at angle alpha 3. And the fourth notch is introduced, let's suppose, at angle alpha 4. And the fifth notch, that is this one, that is introduced at angle alpha 5. And this is centered at the angle of pi by 2. Similarly, if you look at these angles from this side, this will be alpha 1, this angle will be alpha 2, this angle will be alpha 3, this angle will be alpha 4, and this angle will be alpha 5. So this waveform is symmetric about this point. If you flip this waveform over here, that is from here to here, you are going to get the mirror image of this one over here. So these two are exactly same, and we have discussed in the last video, right? And now if you look at the negative portion of this one, so that negative will be having the notches at the same angle. This will be angle alpha 1, this will be angle alpha 2, this will be angle alpha 3, this will be angle alpha 4, and this will be angle alpha 5. And similarly over here, this will be angle alpha 1, this will be angle alpha 2, this will be angle alpha 3, this will be angle alpha 4, and this will be angle alpha 5. So we need to calculate these angles alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 to eliminate a certain set of harmonics. So that angle, if we set over here in this diagram, over here, if we generate a pulse for the switches according to this waveform, because we want, let's suppose, this plus VDC at the output. So what we will have to do? Now let's go back at the circuit diagram and let's see how it is going to operate. If we are going to turn on these two switches, what will be the load voltage? The positive voltage will be applied across the load, plus VDC, right? When this pair of the switches in the on state. Now if I turn off these switches, so there will be no voltage across the load, that will be at 0 level. Now if I turn them again on, so I will be getting plus VDC across the load again. Now if I turn on the opposite switches, these one over here, so what I will get across the load? That will be minus VDC. Why minus VDC? Because now the polarity across the load will be reversed. Now it will be connected with the negative terminal of the source, and this point will be connected with the positive terminal of the source. So the load voltage polarity is opposite if you are going to turn on these switches with respect to these two switches. So if I go back to the voltage waveform, in order to get this voltage waveform, this one, I will have to, let's suppose, turn on switch S1 and S3. Let's look at the numbers. So S1 and S4, sorry, this is one pair, S1 and S4. When this set of pair will be turned on, you will be getting VDC, because that you can see over here. This is S1 and this one is S4. If these two are turned on, you will be getting plus VDC. And if we are going to turn on S2 and S3, you will be getting minus VDC across the load. And if these switches are off, you will get the 0 volt across the load. So we have these three combinations over here, and we will be using those ones to generate our voltage waveform. So now if I go back and look at this one, over here you can see, to get this voltage, I will have to turn on S1 and S4. Similarly over here, I will have to turn on S1 and S4, and to get the 0 voltage, I will be turning off all the switches. And how to get this voltage? This will be obtained by turning on S2 and S3 switch, the opposite switch, with respect to these ones, S1 and S4, right? So now by turning on the switches S1 and S4, I will get the positive voltage plus VDC, and if I turn these one off, I will be getting the 0 volt, and if I turn on S2 and S3, I will be getting minus VDC. So now I will have to turn them on at a particular angle. I will have to turn on the switch S1 and S4 starting from this time till this time in order to get this voltage at the output. Then I will have to keep all the switches off for this interval, and then I will turn on the switch S1 and S4 again from this time till this time. and then I will have to keep them off, and then I will turn them on for this interval for a quarter cycle, because the quarter cycle is completed over here. So now we need to generate these pulses for the switch S1 and S4. This will be the pulse train for that one, that will be amplified. And for the switch S2 and S3, I will have to generate the gate pulse like this, because when this gate pulse will be applied, these switches will be turned on when we will be getting the negative voltage across the load. So this will be the gate voltage waveform for the switch S2 and S3. They will remain off in this, the positive half cycle. They will only be turned on in the negative half cycle part, right? So now if I go and look at inside the blocks, these controller blocks, those we have used to generate these pulses. So first of all, let's discuss this one, the positive half cycle block. So the internal diagram is shown over here. So what we are doing over here, this is the simulation time t, and this is the time period of our output voltage waveform. So what we are going to do over here in this block, what is being done? So if you consider the time variable, that will be increased as the simulation will be running, this time will be increasing. Now we are taking its modulus with the time capital T. And what is the value of capital T? As I told you, we are working it for 50 Hz, so this is 0.02 second, or that is equal to 20 millisecond, right? So now after every 20 millisecond, what is going to happen? When the time reaches to 0.02, this will be becoming 0, the output of this block, and then it will be starting again from here, and once it reaches to 0.02, then it is going to reset, because we are going to take the modulus, right? So the output voltage waveform will be this sawtooth waveform, and what will be the time period of this one? This will be of 0.02, and what will be the magnitude at which it will be reset to 0? That will be 0.02, this one, right? So height will be 0.02 in the time interval 0.02, because after 0.02, what's the modulus? The modulus is going to become 0 over here. So as the time will be progressing, we are taking the modulus with 0.02, it will be increasing, and over here it is going to become 0 and so on. So this is our output voltage waveform, output voltage waveform over here that we will get. Okay, then we have given the gain of this one. So if you calculate 360 by 0.02, so that is equal to 18,000, and if you multiply this 0.02 with the 18,000, what you are going to get? You are going to get 360. So now basically what waveform we will be getting over here? A sawtooth waveform whose time period will be equal to, this time period is 0.02, and what's the magnitude? Varying from 0 to 360 degree. Basically we have converted it in terms of the angle, right? So this is of 0.02 and varying from 0 to 360 and so on. So we will be getting this waveform at this point. So this is generating, you can say, a sawtooth waveform, and then we are going to multiply it with the gain 18,000, so that it is mapped from 0 to 360. So that's what we are going over here. Now just look at this block, this one, what it is going to do. It is taking the sawtooth waveform as an input and the two limits, A1 and A2. So how it is going to work? We understand that one with the help of this diagram. Inside that block we have this diagram. So if I say that I have the sawtooth waveform like that we have generated before, right? So let's suppose that this lower limit is 0. We are going to enter 0 over here. So what you will get, what this block is going to do, it's a logical operation. It is going to check that if your sawtooth waveform is greater than this value, it is going to give you logic high at the output, that you can say equal to 1. And if your sawtooth waveform is less than this limit, it will be giving you 0. So what will be the output volt output of this block over here? What it is? If I am going to enter the 0, if I am going to enter the 0, 0 is definitely less than the sawtooth waveform. So right from the beginning, I will be having this output. Let me mark at point 1. At point 1, I will be having this output. And what about if I say that this is 0.01? What was the time period of this one? 0.02, right? So if I say that I am going to enter 0.01 over here, it is getting this value from somewhere outside the block. So what will be the output over here at point 2? Let me mark it point 2, this one. So what will be the output over here? This output will be logic high if your this value that is coming from the upper port is less than the sawtooth waveform. If that is the case, then the output will be logic high, and if the condition is false, you will be getting output 0. So let's suppose that this value is 0.01. So what about the condition in this interval? Let's suppose this is the point of 0.01 second on the time scale. So up to this point, your upper value is higher than the sawtooth waveform, because you have entered the 0.01, right? If I consider that this height is 0.02, or if you consider in terms of angle, as we have developed this one in terms of angle, so let me write it over here that it is going to vary from 0 to 360, and then instead of 0.01 I am going to enter 180 degree over here. So if I enter 180 degree over here, so up to 180 degree, what about this condition? What about this condition? It is true or false? 180 is being applied over here, and it will give you true if your sawtooth waveform, if this waveform is less than this 180, right? So this block, this particular block is going to give you the output like this, that it will be giving you logic high up to this point, and after that this condition is going to become false, so its output will go to 0. So this is the output at the point 2. Now if you perform the AND operation of this one, the AND of these two signals, so what you are going to get at the output? Let me select some different color to represent that one. So that will be this one, because over here this one is 1, this one is 0, so your net output is 0 because of the AND operation. So you will be getting this pulse according to these limits. The lower limit was 0, that you can see over here. It started from 0 and then the upper limit is 180. So you will be getting this pulse. Now if I say that I have the lower limit of, let's suppose, 60, and the upper limit of, let's suppose, 120. So how this block is going to work? This is going to compare two lines with this sawtooth waveform. So let me draw over here that we have the line of 60 degree, let's suppose somewhere over here, right, and the other line is of 120 degree, that is over here. Just I'm going to assume. Okay, so when the first condition is going to be true, this will be true when your sawtooth, this will be true when your sawtooth waveform, is greater than the lower value. So now if I take, let's suppose the green color for this. So we are comparing it with the 60 degree, and the sawtooth waveform is once it is greater than the lower value, then there will be the output. So up to this point, sawtooth waveform is lesser than the 60 degrees, so it will be 0. And at this point, this will be turned to logic high. The output will go to logic high, right? And over here, it is going to become 0 again, and then it is going to become logic high. So this is the output. This is the output at this point. Let me mark it point 1, right? And then what about the output of the second block? Let me mark it point 2. Its output will be true if sawtooth waveform is less than the upper value. So its output voltage waveform will be like that up to this point. It will be logic high, and after that this 120 is less than the value of the sawtooth waveform, so it will go to level 0, and then it will go to level high over here and will remain at level high up to this point, and then will go to 0. Now if you take the AND operation of these two, so what you are going to get? The AND is this part. So you will be getting a pulse starting from the angle of 60 degree to the angle of 120 degree over here, right? So similarly over here, you will be getting the pulse from 60 to 120 degree. So whatever will be the lower limit and the upper limit, that will extract a pulse from the comparison of these limits with the sawtooth waveform. So in this way you can generate a pulse at the required level. So if I go back and look at this circuit over here, let me remove the previous writings. So I'm going to clear the page. Okay, so now what will be the output of this block, the first block? It will give you a pulse based upon the sawtooth waveform that was generated from here. It will consider its time period equal to 360 degree, and it will give you a pulse from A1 to A2. Let's suppose this is point A1, this is point A2. Let's suppose this is the half cycle, or rather quarter cycle. It is pi by 2 point of the output voltage. So we are going to get this pulse, and then from this block we will get the pulse from A3 to A4. Let's suppose these angles are specified, A3 and A4, and then we are from this block we are going to get the output like that. This is A5 and this is up to 90. So starting from here, this is up to 90. So we will be getting this pulse. So we will have to specify these angles to get the quarter cycle. And then over here, from this block, what are the limits? From 90 to 180 minus A5. So how to adjust this one? Just go and look at this one. We are talking about this one. Half cycle, a quarter cycle is completed. Now about this one. What should be the limit for this one? The limit for this one should be starting from 90 till the point. This is the point of 180. So from 180, if you subtract this alpha 5, so what you are going to get? You are going to get this angle. So we are going to generate a pulse from 90 to 180 minus alpha 5. Then the second pulse, that is from here. That is 180 minus alpha 4 to 180 minus alpha 3. That will give you this interval. That is from here to here. And then for this, what you will have to do, 180 minus alpha 2, and this will be the lower limit, and the upper limit will be 180 minus alpha 1. So in this way you will get this set of pulses from these blocks. Right, so that you can see 90 to 180 minus alpha 5, then 180 minus alpha 4 to 180 minus alpha 3, then 180 minus alpha 2 to 180 minus alpha 1. So adding them all together will give you the complete waveform for the positive half cycle of this particular selected harmonic elimination technique. Right? So we have constructed the pulse train for the positive half cycle of the output voltage waveform. Similarly, if we make a copy of it, of this block diagram, and we adjust these limits A1, A2, A3, A4, A5 and 90 and all of these, so we can get a pulse train for the opposite switches now. Which switches? This one, these two, because these are to be switched in the negative half cycle, and these are to be switched in the positive half cycle. Positive half cycle, and this one is for the negative half cycle. So which type of PWM it is? Output voltage it is. It is the unipolar output voltage that you can see. We are switching between 0 volt and plus VDC, then 0 and then plus VDC, then 0 and then plus VDC, then 0 and then plus VDC, and so on. Up in the half cycle we are switching between 0 and plus VDC, and in the negative half cycle we are switching between 0 and minus VDC. So it's a unipolar output voltage waveform. So at the moment we are discussing unipolar selected harmonic elimination technique, right? Okay, so we have discussed about the positive half cycle. Now we talk about the negative half cycle. Here you can see the block diagram for that one. So first pulse, now we are going to generate the pulse for the switch S2 and S3, and this will be logic high from this point to this point for S2 and S3. So what is the angle? Angle is alpha 1 and the other one angle is alpha 2. So we will be setting the limit 180 plus alpha 1, 180 plus alpha 2. Right? Because we are up to this point the angle is 180 plus alpha 1 will be the starting point of this, and 180 plus alpha 2 will be the ending point of this pulse, this part. Right? And for this what will be the set of limits? 180 plus alpha 4, alpha 3, lower limit, and the upper limit 180 plus alpha 4. And for this part up to the quarter cycle, that is up to the angle of 270 degree, so that is 180 plus alpha 5 to 270. So that you can see over here. The second pulse is from alpha 3 to alpha 4 with the addition of 180, and the next pulse is from alpha 5 to 270. So quarter cycle of the negative cycle, half cycle, and similarly the next quarter cycle, that is this one, that is starting from this point. This is the angle of 270 degrees. So from here, what is this one? 270 to 180 minus alpha 5. So starting from 270 to 180 minus, 360 minus alpha 5, because this is the point of 360 degree now. We are calculating the angles from here. This is basically, this is the point of 360 degree. So from 360 degree, if you subtract this alpha 5, you will be getting this angle from this reference point. Right? So now 270 to 360 minus alpha 5, and then 360 minus alpha 4 to 360 minus alpha 3, and then 360 minus alpha 2 to 360 minus alpha 1, and adding the pulses coming from here, right, and the pulses coming from here, you will get the pulse train for the switches. Which set of switch? The switch S2 and the S3. Those will be applied to these switches S2 and S3. We have generated the pulse set for this one, right? So now if you apply these gate pulses from here, the positive half cycle pulses will be coming from this block, and the negative half cycle pulses will be coming from this block. And have you seen these ports S1 and S4? These are for the positive half cycle. In the positive half cycle, the pulses will be applied at S1 and S4. And in the negative half cycle, we will be getting the pulses, and those will be applied to switches S2 and S3. During the positive half cycle, the output from here will be 0. because we have set the times like that. Only the pulses will be generated in these limits, and in the negative half cycle the output from this block will be 0, because again you can look at the duration of the pulses. Okay, so now if we want to get this waveform, how to generate this pattern, we will have to set these angle limits. Now how to calculate these angles? These angles are calculated according to the set of harmonics we want to cancel. So now we are going to discuss that how to get these angles. Rather, we have already discussed in the previous video. I will briefly revise that one. Okay, now let's look at this waveform. Here you can see the angles for the voltage waveform, as we have already discussed: alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. These angles are to be adjusted in order to get this waveform. And similarly over here, alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5, because this waveform is symmetric about pi by 2, and similarly it is also symmetric about 3 pi by 2. So whatever the waveform you have in this part, if you flip it about this point, center point, and invert, then you are going to get this negative half cycle. So it's a symmetric waveform. Okay, so now we have seen that how we will adjust these angles in the simulation in our controller block diagram. Now how to get the values of these ones? We have discussed in the last video about the equation for this particular selected harmonic elimination technique for the cancellation of certain harmonics. So that is, in general, is this one: cos of n alpha 1 minus cos of n alpha 2 minus plus cos of n alpha 3 minus cos of n alpha 4 plus cos of n alpha 5. That should be equal to 0 for that particular harmonic which you want to cancel, because n is representing the harmonic number, right? So for detail of this equation, how to drive that one, you can refer back to the last video. Okay, now let's suppose that I want to set my fundamental component equal to m into pi by 4, where m is my modulation index, right? Okay, so if I want to keep my fundamental equal to that one, I will consider this n is equal to 1, that you can see over here: cos alpha 1, then this term will become cos alpha 2, cos alpha 3, cos alpha 4 and cos alpha 5, considering n equal to 1. I will get this equation, and I want to set my fundamental equal to m pi by 4, so I have set equal to that one. Now I want to cancel the third harmonic, so I will be replacing this n with 3. So taking n is equal to 3 in this equation, so I am going to get this one: cos of 3 alpha 1 minus cos of 3 alpha 2 plus cos of 3 alpha 3 minus cos of 3 alpha 4 plus cos of 3 alpha 5, and that should be set equal to 0. Why? Because I want to make the third harmonic 0 in the spectrum of the output voltage waveform. Now let's take n is equal to 5 in this equation, and we write down this equation. That will be cos 5 alpha 1 minus cos 5 alpha 2 plus cos 5 alpha 3 minus cos 5 alpha 4 plus cos 5 alpha 5, and that will be equal to 0 because I want to keep the fifth harmonic 0. Similarly, for the seventh harmonic, we can write down this equation and we will set it equal to 0. And for ninth harmonic, we will set up this equation. So now if we work out these angles, that is alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5, so from the spectrum, our third, fifth, seventh and ninth harmonic will be gone. That will no more be present. That will be cancelled because we have set that one equal to 0. And the magnitude of the fundamental will be according to that one, that is modulation index into pi by 4. Right? So basically, if I talk about the harmonics, I am cancelling third, fifth, seventh and the ninth harmonic from the spectrum of our output voltage waveform across the load. So now we are going to set it equal to A1 in our simulation. This is our A2, this is A3, this is A4 and this one is A5. So if I set these values in the simulation block, And if I run this simulation, I will be getting this waveform where this angle is alpha 1, this angle is alpha 2, this angle is alpha 3, this angle is alpha 4, and this angle is alpha 5. So I will be getting the waveform. This is the load voltage waveform of the inverter output, and I have sketched the spectrum along with this. So here you can see we have the fundamental component here, n is equal to 1, and then we have n is equal to 2. Third harmonic is absent because we have set equal to 0 in this case. Then fourth harmonic will be 0. Okay, so all even harmonics will be 0. Even harmonics will not exist. Why? Because we have the half wave and quarter wave symmetry in the output voltage waveform. So that's why all the even harmonics will be 0 because of the waveform symmetry. Only odd harmonics will be there, and from that set of odd harmonics we are going to cancel which set of harmonics? We are going to cancel the third harmonic, fifth, seventh and ninth, and that you can observe from the spectrum of that one that I have obtained from the Matlab. Your fifth harmonic, n is equal to 5, and its magnitude is equal to 0, right? And what about seventh? When n is equal to 7, you have the 0 magnitude. Similarly, when n is equal to 9, you have the 0 magnitude. So all of these harmonics are no more present in the output voltage waveform of your inverter. So that's why we are going to call it SHE PWM, that is selected harmonic elimination PWM, because you have selected the angles of these notches in such a way that now you can cancel the particular set of harmonic that you desire. And in this particular case, we have cancelled the third harmonic, fifth harmonic, seventh harmonic, and the ninth harmonic from the spectrum of the output voltage waveform. We have the harmonics of the higher order, right? And what is the advantage of cancelling these lower order harmonics? Higher order harmonics requires reduced filter size. The inductor size and the capacitor size in the filter is reduced because of the high frequency. So low frequency harmonics, which requires the high size inductor and the capacitor, those are eliminated, so we can easily filter the output voltage waveform of the inverter. And it's the unipolar technique. It's written bipolar over here, so it should be unipolar. And the RMS value of this will be 76.88, and the total harmonic distortion that is observed in this one is 42.759%. Okay, so this is the spectrum of the output voltage waveform, and for the code of this Fourier analysis of the inverter waveform, you can see the video of the Fourier series analysis of the inverter waveform shared on the channel. Okay, now let's quickly go through the simulation in the Matlab, and then we conclude our video. Okay, so here is the Simulink model of what we have already discussed. This is the H-bridge inverter. Here you can see the load. It's the voltage measurement block. This is the scope block, and this is saving the signal in the form of a variable in the workspace. And here you can see the conversion block. Here the gate pulses will be displayed. This is the controller block for the positive half cycle. This one is the controller block for the negative half cycle. So if I look at inside, we have discussed this block in detail. This is generating the sawtooth waveform, and then we are going to generate the pulse with the help of this simple logic. Sawtooth waveform is coming from here. We are going to specify upper and the lower limits, and with the help of this AND operation, we are going to get the pulse between this lower limit and the upper limit. So this is repeated in all of these blocks, and whatever set of pulses we are getting from here, we are going to add them together over here and with these ones, and we are going to apply these pulses to the switches S1 and S4. This one is the go-to block. This signal will be picked up from here and will be applied wherever you will be having the from block of the same tag, and that you can observe over here. It is connected over here. This is the from block, So S1 signal will be applied over here, and the same signal will be applied at the S4. And similarly, if we talk about S3 and S4, S3 and S2, they will be taking taking the signals from their go-to block and will be applying it over here, and that will be from the negative half cycle. So it is exactly same, positive half cycle and the negative half cycle, but you can see over here A1 plus 180, A2 plus 180, A3 plus 180, A4 plus 180, and so on up to 270. And then similarly for the last quarter cycle of the negative half cycle waveform, and those are applied to S2 and the S3, and this is the block generating the sawtooth waveform. In terms of angle, its time period will be 0.02, but its magnitude will be changing from 0 to 360 in terms of the angle, so that if we specify the angles over here, we can get the pulse of the required angle, because basically we have related the time with the angle with the help of this sawtooth waveform that we are getting from here. Okay, so we are getting the signals from here, and we are converting its data type with the help of these two blocks just for the display. Otherwise you can directly put them on the switches. So now let's look at the voltage waveform that we are going to get from here. Here you can see this is the waveform that we have obtained. First of all, look at this one. The first one is the difference of these two, whatever we are getting over here minus this. So you will be getting the output voltage waveform, but scaled from -1 to 1, because we are getting the signal of 0 to 1 at over here and over here. And on the second channel we will be getting the signal of the positive half cycle, and on the third channel we will be getting the signal of the negative half cycle. So now let's look at this waveform that you can observe over here from 0 to 1. This is the angle alpha 1, this is at angle alpha 2, alpha 3, alpha 4, and alpha 5, and this is the end of the quarter cycle at pi by 2, and then the mirror image of that one, and then the flipped and inverted version in the negative half cycle. So this will be our output voltage waveform. In this you can see the gate pulses for the switch S1 and S4. So when S1 and S4 are turned on, you get output voltage waveform, and in the output of the inverter, this will be equal to whatever the DC source you are going to connect, either 100 volt, 200 volt, 300 volt, whatever you are going to connect, that you will get over here, right? So these are the gate pulses for the switches S1 and S4 in the positive half cycle according to the angle, and these are the gate pulses for the switch S2 and S3, because S2 and S3 will be turned on over here, so our output voltage will be equal to minus VDC. When they will be turned on again, so you will be getting minus VDC. So when the switches are turned on S2 and S3, you will be getting this voltage waveform. So these are the gate signals for this particular case. Okay, now these signals are applied over here, so you can look at the output voltage waveform, that is this one, and that is just a magnified version of what we were seeing earlier. Let's suppose that the DC voltage source is of 100 volt, so we will be getting this as an inverter output voltage waveform, and then we are going to store this value in the variable f. So now we will run the Fourier series code looking at this variable f, and then we can display the spectrum of the inverter output voltage waveform. Okay, so here is the spectrum Fourier analysis. Using the Fourier analysis, we have stored this variable f in the workspace, and if I am going to sketch that one, plot that one, so this is our voltage waveform, and here you can see the spectrum of this particular waveform, and we were cancelling the third, fifth, seventh, and the ninth harmonic, and those are absent from the spectrum of the inverter output voltage waveform, right? So this is basically entered in the model properties. If you right click and go into the model properties, so here you can see the callbacks. Callbacks may be used to initialize your functions or use your function at the end of the simulation. So here you can see the initialization function. In the initialization function, I have set up all of these values which we have calculated. So A1, A2, A3, and A4, these are specified over here. This code I will discuss in the next upcoming videos, because we can calculate these sets of angles with the help of the Newton Raphson technique or some metaheuristic technique, because the equations which we were discussing previously, which are used to find out these angles, which are basically these ones. So these are the transcendental equation, and you will have to use some iterative technique to find out this alpha 1, alpha 2, alpha 3, and the alpha 4 and alpha 5. And you can use Newton-Raphson technique, you can use Gauss-Seidel, you can use meta-heuristic techniques to find out these angles. And once you find out these angles, you can set up in your inverter simulation, and you can generate the gate pulses, and you can get rid of the particular set of the harmonics. You can cancel 10 harmonics if you are able to solve the 10 equations simultaneously, and you are able to find out the solution for these angles, right? So in the next upcoming video, I will discuss about this code. This is basically the Newton-Raphson code that is going to calculate the angles for particular modulation index, and for the cancellation of certain harmonics. So, but for this video, am just limited for the basic operation. So, 5 angles which are calculated using the Newton-Raphson to cancel 4 set of harmonics and to get fundamental equal to m pi by 4. So we have these angles, right? So similarly, if you look at the stop function, so if I click over here, so here you can see I have written certain code, and that code is basically reading the signal from here. We have stored the signal in the form of the you can see over here, structure with time. So structure with time is there, it has the information of the time and the information of the signal. So now let's look at the Fourier series window again. Okay, sorry, moving towards the we were at the model properties. Okay, so in the model properties, taking the signal f from here, f dot time, f dot signals dot values, I have obtained the values for that one, and then I have executed the code of the Fourier series. So Fourier series is developed, all the harmonics are calculated, and then those are displayed over here at this graph. So for the detail of that, you can see the video related to the Fourier series analysis code of the power inverters. Right. So if I conclude this video, what we have done in this video, we have seen that how we can simulate a selected harmonic elimination technique in the Simulink, and we have seen that how we can generate the pulses, how those are applied to the half bridge inverter, and the voltage waveform of the selected harmonic elimination PWM based inverter, and then we have seen its Fourier analysis. For the unipolar, if you look at this output, it's a unipolar one, right? 0 plus VDC, 0 plus VDC, and in the negative cycle we have 0 and minus VDC. So in the upcoming videos we will discuss the bipolar implementation as well, and more about selected harmonic elimination technique. So that's all from this video. Thank you very much. One more thing, that you can download the simulation from the MathWorks. I will upload it on the MathWorks, and you can search by my name and you can find out the simulation over there. Thank you very much.